In the last lesson, far field meant one specific simplification root. A bounded source seen from far enough away could share one common amplitude distance, while the remaining source-dependent phase stayed inside the integral. Now we keep that same logic, but the source is no longer a point. The dipole itself becomes the bounded source we have to evaluate. Place a thin dipole on the z-axis and keep the observer at spherical direction r, theta, phi. Each current element at position z' contributes to the observer through a slightly different path length, so the dipole is still bounded, but it is not collapsed. The real question is how to keep the geometry readable without carrying the exact path law everywhere. That is exactly where the far-field approximation enters. The exact distance from a source point to the observer is written as r of z'. In the far field, we replace that exact law by r minus z' cosine theta, and we pull 1 over big R outside as 1 over r. So amplitude becomes common, while phase still remembers where the source point sits along the wire. Once that shortcut is applied inside the vector potential, the dipole problem becomes a line current integral. The common factor e to the minus jkr over r sits outside, because every source point shares the same far observer. Inside the integral, we keep the current distribution and the source-dependent phase term e to the plus jkz' cosine theta. That remaining integral is the part that builds the pattern. For the electrically short dipole, we make one more simplification. The current is treated as approximately uniform over the short length, and the phase variation across that tiny wire is also mild. Then the integral reduces to I0 times L. After the usual field conversion, the far field becomes E theta proportional to e to the minus jkr over r times sine theta, with the strength factor j eta k I0 L over 4 pi. That sine theta term is the pattern story. Along the dipole axis, theta is near 0, so sine theta is also near 0, and the radiation fades. At broadside, theta approaches 90 degrees, sine theta reaches its maximum, and the dipole radiates most strongly. This is the classic donut-shaped dipole pattern in far-field form. So the short dipole far field can be read in 3 layers. 1 over r gives the geometric spreading. E to the minus jkr gives the propagation phase. And sine theta gives the directional strength that turns the dipole into a pattern rather than a uniform radiator. This lesson worked because the source was still finite and bounded. In the next lesson, once the source becomes much more extended, the same shortcut stops being the natural first move. That is where stationary phase comes back into the story.